In this last example, we're going to go through everything that we know from this chapter 4 of calculus. So I want to sketch the graph of f of x equals 4x minus 3 divided by x squared. So I am going to find my domain, my asymptotes, find the first derivative, find out everything that that first derivative is telling me. Second derivative, find out everything that that second derivative is telling me. Compile that all that information at the end, and then make a sketch of my graph. So let's get to it. We need to start by looking at our original function f of x, and how about I do that in black here. I'm going to, first of all, worry about the domain a little bit because we have a rational function. My domain in this case, I'm going to take my denominator, set it equal to 0, x squared equals 0. Solving that will give me x is equal to 0, or rather x cannot equal 0. My domain is technically negative infinity to 0 and 0 to positive infinity. It's all numbers except for 0. The other thing that I want to check with this original function, and we haven't done this in a little bit, we have done this, but not since chapter 2, I want to think about my asymptotes. What sorts of asymptotes do I have? Do I have any vertical or horizontal asymptotes? For vertical asymptotes, remember, those occur when your denominator is equal to 0, but your numerator is not. So I would encourage you to factor as much as possible before you start to think about vertical asymptotes. Here in our case, we can't factor this any further, so we're just kind of stuck with it as it is. Vertical asymptotes, we'll take that denominator, any factors that are left over after we cancel common factors in our numerator and our denominator. Take that denominator, set it equal to 0. This should look awfully familiar. Hey, we end up with x equals 0. So we have a vertical asymptote at x equals 0. And let me even just say this. I have a vertical asymptote at x equals 0. So that's why 0 is not included in our domain, because we have a vertical asymptote there. The other thing that I want to look at here is I'll want to look at horizontal asymptotes. And there's a few different ways that you can think about those. For horizontal asymptotes, some of us were using the shortcut of looking at the degree of the numerator and the degree of the denominator and comparing those. The other thing that we could do is we could look at the limit as x approaches positive or negative infinity. It shouldn't matter which one. We'll say as x approaches positive infinity of our function, 4x minus 3 over x squared, because this is actually how a horizontal asymptote is defined. So here, let's see, I can look at just the limit of the ratio of the leading coefficients of the numerator, just 4x, and then the denominator, which is x squared. Here I can cancel a like power of x, so limit as x approaches infinity, I'm left with 4 over x. If x is approaching positive or negative infinity and I'm left over with any positive power of x in the denominator, this goes to 0. So that means I have a horizontal asymptote at y equals 0. So this is everything that my original function can tell me, and this is everything that I'm going to ask you to find here. We have our domain, we have our vertical asymptote, we have our horizontal asymptote. That's pretty much everything that I'll ask for. My math lab in our textbook asks you to find the x and y intercepts. I'm not going to worry about those. They are important points, yes, but I would rather focus on the calculus aspects of this problem. So we've gotten everything that the original function can tell us. Let's go ahead and work with the first derivative. And if I'm going to take the derivative of this function, I need to use the quotient rule. So f prime of x here says low, that's going to be x squared. D high, derivative of my numerator, is 4, minus high, that's 4x minus 3. D low, derivative of my denominator, is 2x. Square the bottom, this is x squared, quantity squared, and away we go. So my numerator, I've got x squared times 4, I've got 4x squared. I'm going to hold off on distributing this minus sign right here. I will distribute this 2, however, on the other hand. Minus, I should have 8x squared minus 6x all over. If I look at x squared squared, if I have a power raised to a power, I would multiply those two powers, so x to the 4th. So what do I want to do here? I want to now distribute this minus sign. Let's make that a plus, and we'll change the signs on those two terms. Combining my like terms, I should have, let's see, negative 4x squared plus 6x divided by x to the 4th. I can simplify this further, though, by factoring an x from my numerator. So let's see, that'll be x. I could factor out a 2 if I wanted to, but I'm not. I'm not going to worry about that. Negative 4x plus 6 all over x to the 4th. We can cancel a power of x. Let's see, I'm left with negative 4x plus 6 divided by x to the 3rd power. Here is my first derivative. Oh boy. So we've got our first derivative. Now, let's see, what can we do next? We probably want to find our critical points next. So we're going to take our first derivative. We're going to say, okay, I'm going to take my f prime of x. We'll set it equal to 0. And then we'll take our f prime. We'll find out where that does not exist. F prime of x is equal to 0. Here we have a rational function, so you can just take the numerator and set it equal to 0. So I will take negative 4x plus 6, set that equal to 0. Here 6 equals 4x. So x is 6 over 4, which is 3 over 2, or if you really want, we'll say 1.5 as a decimal. Places where f prime does not exist, here, again, I have this rational function right here, so I can just take the denominator, x cubed, and set that equal to 0. Actually, let me just move this over here so I'm not wasting so much space. So f prime of x does not exist. I'm going to take the denominator, x cubed, set it equal to 0, gives me x equals 0. So I have one critical point, x equals 3 halves, and one partition number, x equals 0. Notice I said this is a partition number, not a critical number, because 0 is not in our domain. If we go back to the beginning of our problem, we said, hey, there's a vertical asymptote at x equals 0. But it's still important. We still want to include that on our sign chart. So here's f prime. Let's see, I have 0, and I have 3 over 2. I'm going to take a number in each one of these intervals and plug them into my first derivative. So why don't we start with, how about negative 1? And let's change our color here just so that we don't have so much blue going on. Let's start with negative 1 here. So let's do this over here. F prime of negative 1. This is negative 4 times negative 1 plus 6 all over negative 1 to the 3rd. So I've got 4 plus 6 over negative 1. This is 10 over negative 1, which is negative 10. So what does that mean? My first derivative is negative. My function must be decreasing on the left-hand side of 0. Now I need a number between 0 and 3 halves, 0 and 1.5, so 1, I think, would work just about as nicely as it possible here. So f prime of 1, this is negative 4 times 1 plus 6 all over 1 to the 3rd. This is negative 4 plus 6 all over positive 1. 2 over 1, this is 2. And in particular, a positive 2. So my first derivative is positive on that interval, means that my function is increasing there. Lastly, I need a number on the right-hand side of 3 halves, on the right of 1.5, so I'm going to pick 2, f prime of 2. This is negative 4 times 2 plus 6 all over 2 to the 3rd. And let's see, this is negative 8 plus 6 all over 8. Negative 2 over 8, which is negative 1/4. Our sign there is negative, so our function is decreasing. The other thing that I would add here, I forgot to make a note of it. Remember, hey, we found 0. What was the behavior there? Well, our derivative did not exist here, so our graph does not exist there. And then at 3/2, we found that by setting the derivative equal to 0. So I'm going to put a 0 right there. So this graph right here, I think, is really important. It tells me a lot of information here. It tells me where my function is increasing or decreasing. So actually, let's start with that. Our function is increasing. Our function is increasing from 0 to, let's just say 1.5, just to avoid any confusion with fractions. Our function is decreasing. Function is decreasing on negative infinity to 0 and 1.5 to infinity. I can look at this at 0. It might look like we have a minimum, but remember that 0 is not in the domain of my function, which means it can't possibly be a minimum. So, okay, 3/2 on the other hand, or 1.5, that is in the domain of my function. So I'm going to take 3/2, and I can look at that and say it's increasing and then decreasing. I see that that local maximum there at 1.5. So I'm going to take 1.5 and plug that into my original function, which I've already forgotten what it is. What is that guy? 4x minus 3 all over x squared. So 4 times 1.5, was that squared? I already forgot. No, 4x minus 3. 4 times 1.5 minus 3 divided by 1.5 squared. There we go. And we can go and get a y value for this. Let me grab my graphing calculator real quick. 4 times 1.5, that should be 6 minus 3 divided by 1.5 squared. I end up with 1.3 repeating. So 4/3 if you want to use fractions and impress your friends with your fraction skills, or 1.3 repeating. So we have a local maximum at 1.5 comma 1.3 repeating. Holy moly. So we know where our function is increasing, we know where our function is decreasing, we know where we have a local maximum. All right, we're done with the first derivative. Let's talk about the second derivative. So I'm going to take my first derivative. I'm just going to copy it down here so that I have it in front of me, because otherwise I know I'll forget it. F prime of x is equal to, and I already forgot it. Oh, there it is. Negative 4x plus 6 all over x to the third. So there is my first derivative. I want the second derivative. So I want f double prime of x. So lucky us, we get to use the quotient rule yet again. F double prime of x here. Let's see, low, that'll be x cubed. D high, derivative of my numerator is negative 4. Minus high, that's negative 4x plus 6. D low, derivative of my denominator, that is 3x squared. Square the bottom, here's x cubed squared. And away we go. So let's simplify this. I'll have negative 4x cubed in my numerator. I'm going to take this 3x squared first and distribute that. So let's see, minus, I'll have negative 12x to the third plus 18x squared all over x to the 6th power. So let's see, I'm going to next distribute that minus sign. So this will be a plus, plus, and minus. And I should have, let's see, 8x to the third minus 18x squared all over x to the 6th. Again, I can factor out, what, a 2x squared. Really, it's the x squared that I want to factor out because I think that'll make my problem a little bit easier. Leaves me with 8x minus 18 all over x to the 6th. We can cancel an x squared from my numerator and my denominator. We're left with 8x minus 18 all over x to the 4th. This is my f double prime of x. Whew. All right. I would tell you we're done here, but that would be a lie, so we got to keep going. We need to now find the partition numbers of our second derivative. So we want to find places where is f double prime of x equal to 0, and where is f double prime of x not exist. F double prime is equal to 0. Again, we have a rational function here. If that rational function is equal to 0, that just means the top part, the numerator, so to speak, is equal to 0. So I'm just going to take 8x minus 18, set that equal to 0, and solve. So here, let's see, 8x equals 18, so x equals 18 over 8, which, what is that, 9 over 4, which should be, 2.25, let's say. We're using decimals most of the way here. So here's a partition number, x equals 2.25. I also want to think about where is my second derivative undefined. Again, I have a rational function, and I want to look at the denominator this time, because if I divide by 0, that's a big problem. So I'll take x to the 4th, set that equal to 0. I would take the 4th root of each side if I wanted to solve this, but hopefully, unsurprisingly, we'll end up with x equals 0. So, okay. We've got our partition numbers for the second derivative. Now let's go and construct our number line. So let's do that. Let's do that in a different color again as well. How about we do that in black? Here's f double prime. Let's see, we've got 0 and we've got 2.25. So I'm going to take a number in each interval, plug it into my second derivative now. F double prime, let's start with, how about negative 1? This is 8 times negative 1 minus 18, all over negative 1 to the 4th. So let's see, negative 8 minus 18 all over positive 1. This is negative 26 over 1, which is negative. So my second derivative is negative. Tells me my function, is not decreasing. It's concave downward, because that's what the second derivative tells me. It's easy to get lost in these problems because there's so much going on here. So I'm going to draw a concave downward graph. Next, I need a number between 0 and 2.25. I will take just positive 1 this time. 8 times 1 minus 18, all over 1 to the 4th. This is 8 minus 18 all over 1, negative 10 over 1. So once again, I have a negative, and my function is still concave down on 0 to 2.25. And finally, I need a number to the right of 2.25. How about f double prime of 3? So let's see, negative 8, not negative 8, positive 8. 8 times 3 minus 18, all over 3 to the 4th power. 8 times 3, I should have 24 minus 18, all over 3 to the 4th. Oh, that would be 81, I believe. 24 minus 18, I've got 6 over 81, which, yeah, sure, we could go and reduce, but really it's the sign I care about. It's a positive 6 over 81. Second derivative is positive. My function must be concave up on that interval. So, okay, let's see, our function is concave down on negative infinity to 0 and 0 to 2.25. Our function is concave up 2.25 to positive infinity. And last but not least, Do I have any inflection points? You bet I do. Look at that. I changed concavity right there at 2.25 from negative to positive. So that means I need to take 2.25 and plug that all the way back into my original function. So let's see, f of 2.25. Oh, let me check. Let me write it in first. 4 times 2.25 minus 3 divided by 2.25 squared. I believe that was my function. Let's see. We said 4x minus 3 over x squared. Yes, that is my function. So let's see. I have 4 times 2.25 minus 3 divided by this guy. I end up with 1.19 if we round to 2 decimal places here. So we have an inflection point at 2.25, 1.19. This is everything important that I've gained from the second derivative in this problem. Oh boy, this is a great problem. We're done finding all of our information, so we found all of our information. Now we just need to put all the pieces together and make our graph. How hard could that be, right? Let's summarize our information here. Our domain, I'm going to see how much of I can do it off the top of my head. Our domain, we said, was negative infinity to 0 and 0 to positive infinity. We said we had a horizontal asymptote at y equals 0. We had a vertical asymptote at x equals 0. Our function was increasing, and here's where I forget some stuff, so let me go back up. Increasing on 0 to 1.5, decreasing everywhere else. So increasing 0 to 1.5. It must be decreasing then on negative infinity to 0. And 1.5 to positive infinity. We said we had a local max, I believe, it's been so long. Local maximum at 1.5, 1.33. 1.5, 1.33. And then all the information we just found from our second derivative. So our function is concave down. Actually, let's do this. This is taking up too much space. Say it's concave down on negative infinity to 0 and 0 to 2.25. It is concave up on 2.25 to positive infinity. We have an inflection point at 2.25, 1.19. Okay, we're almost there. So let's make a coordinate axis. I'm going to make mine look something like this. And let's see, most of our numbers are relatively close to 0, so we'll say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. How about that? So I am going to start, I think actually I'm going to start with my vertical and horizontal asymptotes. We have a vertical asymptote at x equals 0. So right here on the y-axis we should have a vertical asymptote. And we have a horizontal asymptote at y equals 0, so right there on the x-axis. The other thing I'm going to look at is I'm going to look at any local extreme values I have, any inflection points that I have. So I have a local maximum at 1.5, 1.33. I'm going to plot that in blue. So 1.5, 1.33. So let's say, you know what? I'm going to exaggerate my graph just a little bit here. Let's say it's up here. And then So I've talked about my local max. That's good. My local, I don't have any local minimums, so I can't talk about those. But any inflection points you have, I think those would be good to plot as well. And actually, before I do that, this point was special. I want to make sure that I label that. That was a local maximum, so I'm going to make sure that I label that and say, hey, that's a maximum. Inflection point, let's see, 2.25, comma 1.19. We should have an inflection point, let's say right around here. And let's move it a little bit over. There we go. And again, I'm going to label that as an inflection point just so I know what's going on there. I should be changing concavity. Holy smokes. Okay. Now I got to graph the function. We're almost there. So let's talk about the left-hand side of 0. I think I would probably start there. On the left-hand side of 0, I don't really have much to work on over here on this left-hand side, and I should say I don't even really know which side it's on. If it's on the top of the x-axis, bottom, is it positive, negative? I don't know. I would look at first the concavity over here, and for that you can always look at your sign chart if you need to. Remember our sign chart for f double prime, we said we had 0, we had 2.25. This is really what I'm interested in looking at. And we said it was negative on the left 2 intervals and positive on the right interval. So our function is concave downward over here. What is our function doing? Is it increasing or is it decreasing? Well, on negative infinity to 0, our function was decreasing. So we're looking at this part of my function right here. So again, I'm going to erase the part that I don't want to look at. And that gives me at least an idea, a starting point. That makes me think that it's probably below the x-axis. So I'm going to go ahead and sketch my function. I think it should look something like, something like this. If you are unsure, you could always take a point and plug that into your function to determine is it going to be below the x-axis or above the x-axis. But as soon as I start to see, as soon as I start to see this sort of shape, let the asymptotes help you out here. I think those really help guide you, right? They kind of, you're just getting closer and closer to the asymptotes on both sides. So use those to your advantage. That's why we find those. They're very, very helpful. All right, what next? Well, in between 0 and 2.25, so in this middle section right here, we said we have something which is concave downward. And this is helpful because we also said, hey, we have a maximum right there. We said we had a horizontal tangent line there earlier. So on this left-hand side of the inflection point, I should have something which is concave downward. Oops, let me try that again. We see, okay, here is, here at this point right there, there's my horizontal tangent line, there's my maximum. And I'm going to run into what seems like perhaps a problem because I say, okay, if it's concave downward, I got to start curving downward, and there's no way for that for that graph to go, right? Some of you might be concerned again about this horizontal asymptote, but remember that you can have a rational function cross a horizontal asymptote in the middle. So here it actually can cross this horizontal asymptote. If you don't believe me, you could always take your function, set it equal to 0. If you were to take your function, just to show as an aside, if you were to take your function 4x minus 3 all over x squared, set it equal to 0. So let's see, we'll get rid of x squared, we'll multiply both sides by that. 4x minus 3 equals 0 gives me 4x equals 3, gives me x equals 3/4. That means it crosses the y-axis, or excuse me, it crosses the x-axis at 3/4. That means it has to cross. So really that point should probably be over here somewhere, but I'm going to go ahead and say that's fine. After that, what happens? Well, after that, our function kind of takes a turn. Now it's concave upward, so it's concave upward. And what else is going on there? So from 2.25 to infinity, well, from 1.5 to infinity, we said our function was decreasing. So our function is decreasing. We're looking at the left-hand side there, looking at something like this. And hopefully this one's going to be a little bit tricky to plot, but hopefully we can start to curve that graph upward a little bit, and then we'll approach that horizontal asymptote. So this one's, I think, very subtle. It's not terribly easy to graph, but you should have your graph sort of curving upward. I'm not even happy with that. Let's try this. So let's try, here's my inflection point. And then afterwards, I'm going to exaggerate the behavior here a little bit. It should be curving upward. It should look something like this. Some of these, I think it is very difficult to capture the exact behavior at those inflection points. Usually, I'm not so interested in that. I'm interested in, can you get the general behavior right? Can you show me where the graph should be in general, concave up or concave down? If it doesn't change concavity exactly at that inflection point, then that's not as big of a deal to me. Whew. So that's it. That's everything in this problem. And this video has been very long, so I'm just going to go ahead and end it right there. If you have questions about this video, please, please, please email me, because this is a great problem. This covers everything that we've talked about in Chapter 4 so far. So if you can follow along with this problem, if you can do one similar to it, you're in great shape. You're gonna do just fine here. So take your time, make sure you practice some of these, and go slowly with these problems.